Hello guys, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of Advanced Algebra. So at this chapter, we are trying to talk about patterns. I'm going to start this topic with two simple questions. Let's see, does it worth it to talk about patterns and how actually we are going to apply it in our algebra course itself? So let's start with questions. So the very first question is this. Imagine that you start with number 3. And then you're going to add 5 each time to that. What number you have at the 10th tone? It means that imagine that you have number 3, you are going to add 5 at each at a time. 3 plus 5, 8 plus 5, 13. And the question is, what number you have if you do it 10 times in a row itself? Let's look at the next question. The next question would say that now, what's the total value of all 10 stones added together? How we can find that? What is the sequence? What is the series among all of that? So this concept or this module is trying to talk about two important parts. The sequence, and after that we are going to talk about the series. We would like to see that if there is any pattern there that I can use in order to apply it in the world of mathematics in order to predict something. For instance, at this question, it's not that hard. Maybe you can just do it by hand without knowing any kind of formula. But what would happen if I ask you, what is the hundredth? What is the 1000 number? How we can do that? Obviously, it's impossible, or at least takes a lot of time. So at this point, we are going to see how we can use this subject in order to ease our life a little bit more. So let's start from simple code to real world power. As I just told you, what are we going to master in this part? We are going to decode the patterns, as I just told you. We are going to talk about arithmetic and geometric sequences. I will tell you what does that mean. The rules behind predictable lists. Then we are going to harnessing the power, arithmetic and geometric series, formulas that calculate massive sums instantly without having that much of a sweat that you think. Then you're talking about the universal language, sigma, notation. Maybe you've seen this guy before, but right now we're actually going to test it in a real-time mode and see that how we can use it. The professional shorthand for writing any sum. Real-world impact. We are going to model the savings, growth, and we are going to depreciation. Oh, sorry about the pronounce. So we are going to see that how actually they're going to affect on our word, and the ultimate pattern is that binomial theorem. I'm going to touch it, but actually this concept is going to be a new one and we will talk about it in our next video. So why this matters, why we are trying to use that, because we are going to, for instance, projecting the salary raises using the arithmetic. We are going to calculate compound interest or card depreciation, and this is about the geometric. And we are going to find the total cost or saving over the time itself, which is going to be about the series. It means that these are the real world application. So let's start with the very basic part, sequences. What is sequences? The anatomy of a pattern. It means that a sequence is an ordered list of terms. For instance, A1, A2, A3, and AN. You see this number of indexes that actually they're going to tell you that at what specific step you're in. This is the first step, the second step, the third step, and final step. So AN simply means the nth term in the list itself. Imagine it would start with A. We are going to add a number one at a time to the next number, and we are going to have this pattern. So we do have some kind of specific formula for that, yet we haven't talked about that, but let's imagine that I know for a fact that my nth number is going to follow up this formula. It means that if I put any number beside the n by using the substitution method, I can find A1, A2, A3, and whatever number that I need. So how I can find the sequence? Simple. Put 1 as the first value, it's going to be 3. 2 as the second value, 7, 11, 15, and you have your sequence. Another some kind of formula about the recursive formula. It means that we can define the next term using the previous one. For instance, if I do have A1 at 3, and I know for a fact that AN is AN minus 1 plus 4, it means that the current number is the previous number plus 4, I can simply predict the next number, right? 3 plus 4 is going to be 7 itself. So that kind of view that you just saw is intuitive. we are going to see that what is happening around us and what is the main question is, and do we have any toolkit in order to answer that or to find a solution for that or not. Then we do have the case that what if the pattern is additive? Right now we are going to talk about arithmetic sequences. So here's the idea. The defining feature is a constant difference. As we just saw in our previous example, for example, the very first example, we will start with the first or beginning number, then we are going to add one number, which means that that guy is constant at a time to the whole some kind of the system. 3 plus 8 plus 5, 13 plus 5 is going to be 18, and so on and so forth. You see that the number that you're adding is not changing at a time. So this number is constant difference, that this guy is going to be added between each consecutive term. It means that between the current term and previous term, the difference is going to be what? Something constant, that we call it as constant difference. So in order to master the formula, we do have an is equals a1, or the very first number, plus 1 sub n subtracted by 1 times d. It means that if we would like to find our current number, the only thing that we need to do is just add the first number plus n minus 1. N means that what is the number that I actually are looking for? Is it 10th number, 20th number, 15th number? What is that? We put it and subtract it by 1 and multiply by a constant value. In words, we are going to start with the first term and add the difference n minus 1 times. So here's the example. Imagine that you do have a sequence that you would start with a1, or the first number is 7. And the a is the common difference, and it has a common difference of d. So d is equal to 3, and I'm going to find the 20th term. Either I can write it down one by one and add 3 at a time to each value in order to find that one, or I can use this simple term. A20 is equals a1. What is a1? 7 plus n subtracted by 1, which is 20 subtracted by 1 times 3. If you do that one, you do have 64 as your final answer. Simple as that. As we just saw, by using the pattern and a very simple formula, which is going to somehow being intuitive for ourselves, we don't have to prove it because it actually makes sense. By using that formula, instead of just writing down all of the numbers one at a time that could probably have some mistake and obviously time consuming, we can find a final number easily without any issue itself. So what would happen if we were talking about summing? If you remember, it was the second question. So we are going to sum it all up in only one step. Imagine that I do have the arithmetic series. I can call it as S of n. S of n is a1 plus a2 plus a3 all to the a plus an. So right now, I would like to know that what would happen, or do I have any kind of formula in order to find the sum of all of them? So actually I do. And I'm going to talk about this formula. So this formula would says that S of n, or subtract all of the numbers from beginning a1 to an, is n divided by 2. Whatever number n is divided by 2. N is the total number of your whole numbers times first number plus second plus last number. So at some point you don't have the an, but you can use another formula. The only thing that you have is the first number and your pattern, or you have the constant difference. The only thing that you have to do, n divided by 2 multiply by 2a1 plus n minus 1 times d. How we got this idea? Because as you know, an is a1 plus a minus 1 times d. If you just put this value inside this equation, you can derive this equation from itself. So at this point, I do have an example. Imagine that we do have a case that I'm looking for the sum of 30 terms for a sequence where the first number is 5 and my d, or constant addition, is going to be 2. How I can do that? It's simple. Which one of these two formulas I have to use? Since I don't have some kind of final number, I can use this one. Or I can find my final number and then use this one. Both of them would be right. So what is the final number, or the 30th number, is going to be 63. a1 plus a minus 1 n subtracted by 1 times d itself, so you do have 63. So S of 30 will be 30 divided by 2, the first number plus last number, and you have your final value is going to be 1020. Simple as that. So what if the pattern is multiplicative? It means that instead of just being additive, that we had 2, 4, 6, 8, we do have as 2, 4, 8, 16, 32, and etc. As you can see over here, instead of just adding something at a time with the previous number, I'm multiplying at a time with, again, something constant. This is something that we call as geometric sequences. It means that the core idea over here is that instead of just adding a number one at a time, we do have something we call it as a constant ratio, or R, which is going to be multiplied between each consecutive term. It means that if you divide your number by the previous one, you're going to have the same number at each time, which is going to be R, or the constant ratio. So the master formula is this: an is the first number times your ratio to the power n minus 1. So let's see an example. Imagine that the value is going to start with 8t and is going to decrease by 20% each step. It means that I'm going to have decremental case. I'm going to have R as 0.75. How we found that 0.75? Because we are going to decrease it 0.25%. 1 subtracted by 25, or 0.25, is going to be 0.75 itself. Find the sixth term. It means that I do have my first number, 80. I do have my R, which is going to be 0.75 to the power of n minus 1, 6 subtracted by 1, and I can find the value that I like itself. So at this point, the value shrinks. Why? Because each step, it has the ratio of less than 1 itself. So the finite geometric series, what would happen that, again, we would like to add all of these things? Obviously, it's not going to be as the same as arithmetic one, right? So the big formula for exponential sum, how is that? The geometric series, or S of n, is the sum of the first n terms. S of n is a1 plus a1 times r plus a1 times r to a1 times r to the power of n subtracted by 1. How we can find that? Simple. The only thing that you have to do is memorize this formula. S of n, or sum of all of these numbers that you had from the beginning to the final, a1 times 1 subtracted by your ratio to the power of n divided by 1 minus r. So imagine that we are looking for the sum. We do have 8 terms of geometric sequence where a1 is 3 and r is 2. Find the sum. How we can do that? What is a1? First of all, try to write down everything. a1 is 3, r is 2, and n is 8. The only thing that I have to do, I have to put it over here. So I do have it as what? I do have it as 8 multiplied by 1 subtracted by 2 to the power of 8 divided by 1 subtracted by 2. If you do this calculation, you have 765 as your final answer. Simple as that. So here's a real question, because as you just saw, if we do have r bigger than 1, apparently our sum is increasing, and if you do it till infinite, you do have positive infinite. But what would happen if you do have shrinking scenario? And what would happen if you're, as we just saw in 2 examples before, if you have it as a number smaller than 1? It means that your number is shrinking. So at this point, apparently, the way, or the more that you go onto this road, you see that your final numbers are going to reach to 0 and until they're going to vanish. So somehow I can say that after some point, or after infinite number of steps, I can get rid of the final numbers, and also can find a formula for that to find the total sum. It's not the actual value, it's very close to the value that we would like. So here's the scenario. Can you sum forever? The magic of convergent infinite series. What is that? An infinite geometric series only has a finite sum. It converges, remember, if the absolute value of the ratio is less than 1, something like this. If the condition is met, the sum is surprisingly going to be simple. As I just told you, the final numbers are actually going to be so small we can get rid of that. S of infinite is going to be a1, or our first number, divided by 1 minus r. How is the example? Imagine that I do have this one. 3, 1.5, 0.75, 0.375 plus till the infinite. And I would like to know that, first of all, can I find any convergency over here? And yes, I can. Why? Because first of all, we are talking about geometric some kind of geometric sequence, and after that my r is going to be half, and we know half is smaller than 1. So the only thing that I have to do, find the first number, 3, divided by 1, subtracted by half, which is going to be 6. It means that something like this is happening for me, convergency. First it was 3, after that 1.5, after that 0.75, and it's going to be something around 0. But if I do have divergence, it means that the number is increasing and increasing, and actually I can't find any number for the final summation of all of that. So here's the interesting part. Rather than just writing down my numbers plus each other, we are going to find a solution. We are going to find a symbol that is going to show this one to me without having any kind of messy condition. The universal shorthand for summation is something that we called as sigma. So sigma is a Greek letter that we are going to use in order to have sum. And not only just by having that, we are going to have this specific condition that we are going to have the sigma, and inside of that sigma, whatever some kind of number or whatever kind of pattern that we do have is going to be expression in k. It means that, as we just saw, for instance, an is a1 plus n minus 1 times d. We are going to have this expression inside of this part. Then we do have two important numbers, n and k. So k equals to 1, most of the time we use that. It is an index that shows that your summation would start from what number, and it's going to be finished at what number. So at this point, we say that some kind of, I do have the summation from that would start from the very first number to the nth number. It could be anything, 10, 12, 15, whatever, that follows this expression itself. So for instance, or for example, I do have the sigma from k to 1 to 4. It means that my k equals to 1 is going to be there, and n is going to be 4 of k2. It means that the expression that I have over here is k2. What does that mean? It means that the very first number is 1. The second number is 4. The third number is 9, and so on and so forth. So k2, by the way, is not geometric or arithmetic. It's just an expression that we do have. So we are going to use that. So simplifying with sigma, rules for pro. So the thing is that we just learned everything, somehow the definition of sigma and how we can write it down, how we can read it. But can we do a couple of rules related to that? So the very first thing is about the linear, some kind of condition or linear characteristic of our sigma. Sigma a plus b, a could be the first expression, b could be the second expression, it would be sigma a plus sigma b. Then the constant multiple. It means that sigma of c times a is going to be c times sigma of a, if I assume c is just a constant number and a is an expression. And also related to that, also beside that, we do have two important formula. It doesn't hurt if you remember them. Sum of constants. If I do have a scenario like that, sigma at k from 1 to n and 1. What does that mean? It means that you are going to add 1 n times by itself. So if you do that, actually that was the definition of multiplication, right? It would be n times 1, it would be n. Some of the first n integers, we know about the integers. Integers means the number would start from 1, 2, 3 till the infinite. So sigma of decay, that we are going to have that as expression. Again, k, why we use k? Because actually k is a number that's going to be changed. N is the final number, and k is the one that's going to start from 1. So I do have 1 plus 2 plus 3 plus 4 all the way to the n. So I do have this kind of formula for that, as simple as that, right? So if you just memorize these two, that would be so helpful. By the way, let's talk about the second formula because it is familiar. If you remember, S of n was n divided by 2 times 2a1 plus n minus 1 times d, right? So let's have it. It's going to be n divided by 2. I'm not sure how many numbers, what is the some kind of final number. 2a1 is going to be 2 plus n minus 1 times d. Again, I don't know about n minus 1, but I know d is 1 because it's going to increase one at a time. This guy is going to be n plus 1, so n plus 1 multiplied by n over 2 is going to give you that one. Again, it is very simple. You don't have to some kind of memorize that. So let's see an example. We would like to simplify the whole idea or the whole thing. How we can do that? As we just learned, we can write down sigma of 2k plus sigma of 1. Sigma of 1 is going to be what? Is going to be n, right? If you assume that it would start from 1 to n. Sigma of 2k is going to be 2 times sigma of k, because we know based on this rule. So sigma of k is going to be n times n plus 1 divided by 2. If we simplify that, you would have something like this, as simple as that. This is the way that we are going to simplify everything like the way we had. So let's connect the dots. Let's see what is happening over here. So let's connect the dots over here. We do have a series of formulas that are just sigma received. What does that mean? Sigma is not just a new math. I just told you sigma is another form that instead of just writing down the patterns between the numbers, or at least write down the numbers, for example, a1 plus 2d, in another form that we call it as just sigma. Sigma is another form of math, right? It's just more powerful way to write the sums we already know, right? Arithmetic operation. We do have a1 plus d plus a1 plus 2d. Instead of just writing down everything like this one to be completely messy, we can write it down like this. K is equals to 1. It means that if I just write 1 as the first number, it's going to be my first number, a1. If I put 2, it would be a2, so on and so forth. So k from 1 to n, a1 plus k minus 1 times d is going to be the sum itself. What about geometric series? The same thing. a1 plus a1 plus a1 times r2. We are going to do the same thing. You do have k is going to start from 0. Remember that, because r to the power 0 is going to be 1. If you start from 1, actually, we are going to miss the very first thing. K is equals 0 to n minus 1, and we do have a1 times r to the power of k. So let's have the real world implication. Imagine that we do have the saving goal. And the scenario is like this. You start by saving $50 in week 1. It means that your first part or your first step of saving is $50. Each week you save $20 more than the previous week. And here's the question. The question is, first of all, we do know about this. D is $20 and A1 is $50. How much will you deposit in week number 12? It means that in week number 12, how much you have in your saving? Simple, right? A12 is going to be 50. I'm sorry, you're going to deposit. That was a complete mistake. It means that at the 12th week, how much money you are going to put inside your bank account. It will be $50 plus 12 minus 1 times 20. It would be 50 plus 11 times 20 and $270. It means that at 12th week, you do have $270 that is going to your deposit into your account. What will your total saving be after 12 weeks? This is a serious problem. So we do have S12, as we know, it's n divided by 2, 12 divided by 2, times the very first number plus the last number. 50 plus 270 is going to be 1920. That's how we can use it in the real world. Let's talk about the value of the car, the geometric decay. Here's a scenario. You buy a car and it would be some kind of $10,000. And its value is going to reduce each year by 15%. This is a shrinking scenario. So here's the model. This is a geometric pattern. Why? Because I do have my car, which has the first value of 10,000, and each term or each year is going to decrease by 15%. Or I can say that my R or ratio would be 0.85. Here's the question. What will the car be worth after 5 years? It means that I'm looking for A5. So A5 would be 10,000 A1 times R to the power of n minus 1, right? So at this point, actually, it's not going to be right itself, because this one should be after the 5 years itself. Oh, actually, that it was right, because we are looking for the value at the start of the 6th year, right? We had as A1, A2, A3, A4, A5, A6. So that was the very beginning value. That was after 1 year, after 2 year, after 3 year, and 4 year, and after 5 year. So actually we are looking for A6. It is very important to understand the question, so be careful. So A1 times R to the power of n minus 1, which is going to be the final value that we have over here itself. So the ultimate pattern, fast expanding with the binomial theorem. So first of all, let me remind you that binomial theorem is a new section or new part that we are going to talk about it in the next chapter. So don't worry about it right now. Try to just understand, to at least see that how we can use it. If you don't get it right now, that is totally fine. So some kind of the motivation that we have, we are going to manually calculate a plus b to the power of 6. If you guys remember that we had a plus b to the power of 2, it was a2 plus 2 plus 2ab. But what would happen if I do have a plus b to the power of 2? A plus b to the power of 3, or a plus b to the power of 4, or in this case, a plus b to the power of 6. Obviously, it would be so confusing to just memorize that. So we are going to see that by multiplying it out is obviously slow, right? Tedious, and is going to be prone to error. There must be a pattern, or there must be a better way. That's why we are going to use that. A plus b times to the power of n equals to sigma of k is equals to 0 to n with binomial of k of n, we will talk about it next chapter, times a to the power of n minus k times b to the power of k. For instance, how we can have a3, a plus ab plus 3, a plus b parentheses to the power of 3, what is going to be the sigma? Let's start with the very first one. The k, or 1 out of the n itself. It would be some kind of k would start from 0. 0 out of 3 is a number 1. I will tell you why next time, so just admit it. 1 out of 3 is going to be, or 1 of 3 is going to be 3. 2 of 3 is going to be 3, and 3 of 3 is going to be 1. So it means that the first coefficient is 1, the coefficient of power 3, b to the power 0. The second one, a to the power 2 times b to the power 1 is 3. The third one is 3 again, and the fourth one is going to be 1. So by this way, by using the coefficients and by using a sigma, I can find a pattern. So there's a secret code actually for that, and we call it as a Pascal triangle, and this is going to be the challenge that we have. So the challenge over here, we can call everything that we just saw, instead of just memorizing that maybe at this point tedious formula, we can have this triangle. We call it as a Pascal triangle. So what is that? Pascal or Pascal. So it means that we can start from number 1. Then we do have a triangle that contains 3 ones. Then for the next step, we do have another triangle that it contains these guys. Then we do have another triangle that contains these guys, and till the end. By having that at n is equals to 0, it means that a plus b to the power 0, I do have as 1. When n is equals to 1, I do have a plus b to the power 1 is a plus b. When n is 2, I do have a plus b to the power 2, which is a2 plus 2ab plus b2. Just like the coefficients, 1, 2, and 1. And for n to the power 3, it's just the way that it was. So we are going to use that. We are going to use the secret code in order to find this thing that we just had in the previous slide. Instead of just using this formula, we can use that one. But in the next slide, actually, or the next chapter, I'm going to show you that how can you use that formula. It's going to be way easier than that. So what we were talking about? We were talking about two important sequence or patterns, the arithmetic sequence or geometric sequence. We saw that actually if you do add, or if you multiply one number at a time to your previous time, you're going to have a pattern. Not only you're going to have a pattern, you can predict that specific number you're looking for, which is the nth number, but you also can find the sum of all of those previous numbers one at a time. Instead of just adding it just by yourself, you are using the calculator, you can just calculate it using the formula itself. Again, try to rewatch the video, and as you can see, I just put a couple of examples where you try to solve all of them, and after that, comment me down below that could you find all of those answers or not. If you couldn't, please tell me. I will try my best in order to help you. If I couldn't, I'll probably make another video to answer all of them. Again, thank you for being here with me. Please share and comment. That would be so helpful to me. My name is Mahmoud Kiasari. Have yourself a great day, night, whatever. See you around.